Place holes uniformly on a circular pattern in CAD. Start by creating the base part and drawing the reference circle for the bolt circle diameter. Use tools like the hole wizard or circle command to define the first hole. Apply the circular pattern feature, specifying the number of holes and equal spacing. Verify angular spacing and add constraints and dimensions to fully define the sketch. Simulate for interference, generate engineering drawings, and export files for manufacturing. This process ensures precision and efficiency in creating bolt patterns. Geometric models are the foundation of CAD operations. They mathematically represent the shape and form of objects, enabling analysis, rendering, and manufacturing. Geometric models communicate complex shapes visually, replacing lengthy descriptions. They serve as the basis for simulations like FEA and CFD, predicting real-world performance. Manufacturing data, such as CNC toolpaths and 3D print slices, are derived directly from geometric models, ensuring accuracy and consistency. CAD technology has evolved from simple line drawing systems in the 1960s to advanced 3D modeling and cloud-based platforms today. Early CAD was limited to basic graphics, but affordable 2D drafting software like AutoCAD made digital design accessible. The shift to 3D solid modeling and parametric design enabled complex forms and rapid changes. Modern CAD platforms support real-time collaboration and AI-driven generative design, transforming architecture and engineering workflows. Designing a gear system for a small robot in CAD involves several stages. Begin with requirements analysis to determine torque, speed ratio, and gear type. Concept sketching explores gear arrangements and housing configurations. Create a 2D layout in CAD to verify ratios and clearances. Model each gear as a 3D solid with parametric features. Assemble components and run motion simulations to verify meshing. Apply FEA for stress analysis, optimize geometry, and prototype using 3D printing or CNC machining. Collaboration tools ensure version control and teamwork. CAD uses Cartesian coordinate systems to position objects precisely. Absolute coordinates measure from the origin, while relative coordinates are based on the last point entered. Polar coordinates use distance and angle for placement. The user coordinate system UCS in 3D CAD allows drawing features on inclined surfaces. These systems ensure accurate placement and manipulation of objects, making complex designs manageable and precise. CAD supports various dimension types, each serving a specific purpose. Linear dimensions measure horizontal or vertical distances, while line dimensions follow inclined lines. Angular dimensions capture angles between lines or faces. Radial and diameter dimensions define circles and arcs. Ordinate baseline and continue dimensions provide reference-based measurements. These tools ensure that every feature is accurately described, facilitating manufacturing and quality control. Data representation in CAD involves storing geometric and non-geometric information mathematically. Wireframe models use vertices and edges, surface models employ NURBS for complex curves, and solid models define complete geometry with topology. Parametric data stores features as parameters and constraints. Accurate data representation eliminates errors, enables scalability, and simplifies modification. Feature-based models update automatically, ensuring consistency across drawings and assemblies. Layers in CAD organize drawing elements by category, assigning colors, line types, and line weights. Layers can be toggled on or off, frozen or locked, allowing flexible control over visibility and editing. Hatch patterns fill enclosed regions with repeating designs, representing materials and cross-sections. They communicate material information and indicate cut sections, following international drafting standards. Layers and hatches make complex drawings clear and informative. In CAD, lines represent straight segments, arcs are portions of circles. Circles are defined by center and radius, and polygons are closed figures with straight sides. Each has real-world applications: wall centerlines, road curves, bolt holes, and floor tiles. Understanding these basic objects is essential for creating accurate and meaningful technical drawings. Creating a room layout in CAD involves setting up the drawing area, adding layers for walls, doors, windows, and dimensions. Draw walls using rectangles and offsets, insert doors and windows as blocks, and apply hatch patterns for flooring. Dimension the drawing and add text labels for rooms. Plot the drawing at the desired scale for printing. This structured approach ensures clarity and accuracy in architectural plans. Rotate and scale a square in CAD. First, translate the pivot to the origin. Apply the rotation formula, translate back, and then scale. For example, rotating a square 60 degrees clockwise and scaling by sx equals 3, c equals 2 changes its coordinates significantly. This process demonstrates how CAD transforms objects mathematically, ensuring precise manipulation for complex designs. AutoCAD's command line is a powerful interface for drawing objects. The circle command lets you specify the center and radius, or use alternative methods like 3P or 2P. The line command allows sequential drawing of segments, ending with enter. The arc command offers multiple ways to define arcs, including start, center, and endpoints. Mastering these commands streamlines the drafting process and enhances productivity. CAD and CAM form a seamless digital manufacturing pipeline. CAD creates precise geometric models, while CAM generates toolpaths for CNC machines. The link is established through neutral file formats or direct integration. With CAD CAM, the 3D model becomes the primary design authority, reducing reliance on 2D drawings. Model-based definition embeds manufacturing information directly in the 3D model, streamlining production and communication. Drawing a 3D machine block in AutoCAD involves setting the workspace to 3D modeling, drawing the base rectangle, extruding it, and adding features like steps, inclined surfaces, and cylindrical pockets. Use commands like extrude, wedge, subtract, and chamfer to shape the block. Apply dimensions and render the model for verification. This step-by-step approach ensures accurate reproduction of complex mechanical parts. Layer in CAD acts as a logical container for drawing elements, each with its own properties. Layers organize elements by type, control visibility, manage printing, and enhance editing efficiency. Locking layers prevents accidental changes, and naming conventions ensure interoperability. Layers are essential for managing complex drawings and maintaining standards across projects. Current engineering leverages CAD CAM for parallel development. Shared 3D models allow teams to access live data, enabling immediate updates and feedback. Design for manufacturability (DFM) ensures manufacturability early in the process. Parallel documentation compresses timelines, allowing procurement and manufacturing to proceed while design evolves. This approach increases efficiency and reduces time to market. AutoCAD offers powerful editing commands. Move displaces objects, copy creates duplicates, rotate turns objects about a base point, scale resizes objects, and trim removes unwanted segments. These commands streamline the editing process, allowing efficient manipulation of drawing elements. Mastery of these tools is essential for professional drafting and design. Transforming a triangle in CAD involves translation and rotation. For example, translating triangle PQR by +4x and +2y, then rotating 90 degrees counterclockwise about the new pivot changes its coordinates. This demonstrates how CAD handles geometric transformations, enabling precise manipulation for design and analysis. Design Manager's choice of CAD system depends on cost, compatibility, functionality, and ease of use. Licensing hardware and training costs must fit the budget. The system should support standard formats for interoperability. Features must match the department's needs, and user interface quality affects productivity. These factors ensure the CAD system aligns with organizational goals. CAD interfaces include command-based, menu-based, and direct manipulation methods. Command-based interfaces are fast for experts but have a steep learning curve. Menu-based interfaces are more accessible but slower. Direct manipulation allows intuitive dragging and resizing but lacks precision. Modern Windows-based CAD uses a hybrid approach, combining menus, command lines, and direct manipulation for maximum productivity and accessibility. Design is the foundation of engineering and manufacturing. It specifies geometry, materials, and performance requirements. Engineering analysis validates designs, ensuring safety and reliability. Manufacturing process planning uses the design to determine tools and sequences. CAD integrates these steps, creating a seamless pipeline from design to production. Without design, manufacturing is impossible. Absolute coordinates in CAD are measured from the origin, ideal for placing features at known positions. Relative coordinates are measured from the last point, useful for drawing connected geometry. Polar coordinates use distance and angle for placement. Understanding these systems is crucial for accurate drawing and manipulation in CAD. CAD enables rapid prototyping through 3D modeling, virtual analysis, and physical production. Models are analyzed for stress and performance before printing or machining. 3D printing produces prototypes quickly, while CNC machining creates metal parts. Feedback from prototypes is used to refine designs, leveraging CAD's parametric capabilities for fast iterations. CAD offers multiple methods for drawing arcs and circles. The three-point arc defines a curve passing through 3 points, useful when center and radius are unknown. The two tangents and a point method creates a circle tangent to 2 objects and passing through a specified point. These flexible tools enable precise geometry creation for complex designs. Geometric modeling is the mathematical representation of shapes in CAD. It forms the core data structure for visualization, analysis, and manufacturing. Models provide precise definitions, serve as input for simulations, and encode design intent through parameters. This enables rapid design iteration and global collaboration, making geometric modeling essential for modern CAD workflows. Rotation transforms an object by turning it about a fixed point, changing its orientation. Movement or translation shifts every point by a displacement vector, changing position but not orientation. In CAD, commands like rotate and move enable these transformations, allowing precise manipulation of objects for design and layout. To apply a hatch pattern in CAD, ensure the area is a closed boundary, set the hatch layer, and use the hatch command. Select the pattern, scale, and angle, then pick points inside the boundary. Hatch patterns distinguish materials in cross-section drawings such as concrete, gravel, and soil. They enhance clarity and communicate material information instantly. CAD supports special effects like gradients and shadows to enhance visual presentation. Gradients suggest 3D surfaces and lighting, while shadows are produced in 3D rendering environments. In 2D, shadows can be simulated by offsetting filled shapes. These effects improve client proposals and architectural visualizations, communicating aesthetics beyond technical accuracy. Polylines in CAD are connected segments forming a single object, while regular lines are independent segments. Polylines can have variable width, support closure, and allow area calculation. Editing a polyline affects the entire entity, while lines are edited individually. Polylines are ideal for borders, flow diagrams, and closed shapes requiring area measurement. Draw a 100 mm x 50 mm rectangle with a circle of radius 30 mm at its midpoint. Use the rectang command for the rectangle and circle for the circle. The midpoint is at 5025, and the circle extends beyond the shorter rectangle side. Dimension both shapes for clarity. This method demonstrates precise placement and dimensioning in CAD. Absolute coordinates are measured from the origin, ideal for fixed positions. Relative Cartesian coordinates are from the last point, useful for connected geometry. Polar coordinates use distance and angle, perfect for drawing lines at specific directions. Mastery of these systems enables efficient and accurate CAD drawing. Rotate an ellipse 45 degrees about its center and move it 30 to the right. Use the ellipse command for drawing, rotate for orientation, and move for displacement. The ellipse's center shifts from 100,100 to 130,100, maintaining its new orientation. This process illustrates CAD's capability for precise geometric transformations. CAD has revolutionized architecture, engineering, and product design. BIM tools enable complex building models, preventing site conflicts. Mechanical engineering benefits from integrated CAD/CAM CAE, optimizing designs before manufacturing. Product design achieves tight tolerances and rapid iterations, enabling mass customization. CAD's impact spans industries, driving innovation and efficiency. Text and annotations in technical drawings communicate information beyond geometry. Labels identify features, leader lines clarify specifications, and title blocks provide essential metadata. Special effects like gradients and shadows enhance presentation, making drawings informative and visually appealing. Proper use of text and labels ensures clarity and traceability. Drawing a line from 1010 to 5010 using absolute coordinates, then moving it to 2030 with relative coordinates demonstrates CAD's precision. The move command shifts the line by a specified vector, maintaining its length and orientation. This technique is fundamental for accurate placement and editing in CAD. Dimensioning in technical drawings communicates size, location, and tolerances of features. It ensures manufacturers produce parts to exact specifications, guides quality control, and forms the legal basis for contracts. Proper dimensioning is essential for accurate manufacturing and assembly, preventing costly errors and misunderstandings. Current CAD limitations include steep learning curves, hardware requirements, interoperability issues, and limited automation. Future trends point to cloud-based CAD, AI-driven generative design, VR/AR integration, and digital twins. These advancements promise greater accessibility, collaboration, and innovation, shaping the future of design and manufacturing. Proper dimensioning in CAD designs leads to manufacturing errors, assembly failures, and costly rework. Overdimensioning creates conflicting tolerances, while underdimensioning leaves gaps in information. Real-world examples like the Mars Climate Orbiter loss highlight the importance of accurate data. Proper dimensioning ensures parts fit and function as intended, safeguarding quality and reliability.